the statement is that SU2 is a double cover of SO3. SU2 is simply connected. It is called the covering group. So this is called a SU2 is said to be the covering group of SO3, and the idea of covering group always is that it has to be simply connected. So sometimes this is also called universal covering group. Let us see the simplest example of a covering group. Consider the abelian group e raised to I theta. I theta. This pen is not good. With theta going from 0 to 2 pi. So this is like the unit circle, and under multiplication so theta and theta is mod 2 pi. Taken modulo 2 pi. So you can multiply group elements, in which case by simple multiplication you will get theta plus theta prime in the exponent. If that number has become bigger than 2 pi, then you subtract 2 pi, it maps it back into this range. So it is taken modulo 2 pi. Now this space is not simply connected because it is a circle, right? You can't shrink circle. So you can, the space is topologically a circle. Called S1 by topology people. S is reserved for circles, for what reason I don't know, but it's S. And that 1 is the dimensionality of that space. So it is a one-dimensional sphere. Circle is not simply connected, it has two classes of loops. Actually, it has many classes of loops. Distinguished by how many times? Actually, I am sorry, okay, as far as this is concerned, it is a circle and only one copy of it. It has two classes of loops. Distinguished by whether they are, so I can take this circle, class 1 starts from here, goes back, goes forward, goes back, goes forward, goes back, goes forward, and comes back to this point. So this is category 1. I can just keep going zigzag back and forth, do a random walk without actually going around the circle. Then such a walk I can always shrink to a point. But the class B is which starts from there, do whatever else you want here, but eventually you go around and then end up here. So this is category 2 loop class. That one you cannot shrink to the first type because you have gone all the way around, and once you have ended, this was the question for the circle also, you start from this point, and if you come all the way around and reach here, that forms a closed loop. Now that loop, if you are allowed to make the beginning and end point disjoint, then of course no magic is left, but the point is that they are connected in the end, makes the closed loop, and then there is no way of shrinking it. So there are two classes of loops and they are distinguished this way. The covering group of the circle or of the U1 is the real line. You open this up and then you allow it to take all the values and don't restrict it by modulo 2 pi. Then topologically, then they are mappable into each other because they are both continua. The one is, both are open sets. You know, you once you have opened up the circle, okay, they are semi-infinite. So it gets mapped onto a semi-infinite line, but you take the whole line to have universality. You take the whole line, but once you open the circle and make it into a piece of the, so what one can say is the real line is an infinite cover, not just a double cover. The SU2 was a double cover, it's only exactly twice as many points. There are 2 to 1 mapping. For an interval which goes to 0 to 2 pi, there are infinite number of such intervals in in R. So R forms a infinite cover. The covering space is R taken as a group with simply addition. So R provides an infinite cover. Countably infinite. Copies of the interval (0 to 2 pi) in R. But it is a simply connected set. R does not contain any unshrinkable loops. There is not, you can keep random walking on R as long as you like, you will never form a closed loop. So much about the story of SO3 and SU2, and now we go to their representations, which actually you already know because you have done quantum mechanics, right? Now to find the representations, there is this standard trick, you use the algebra. So remember we have, and I will use for the time being the J notation, the complex notation, because in both tau and L algebra fall in the same class. Okay. One can convert this into, so now suppose we choose a vector space such that, and we choose the eigenvalue of J3 to be the basis. So now you will ask me what is the dimensionality of this vector, and for the time being we will not declare what its dimensionality is, okay, and we will find out what the dimensionality is, because the dimensionality is going to be the dimensionality of the representation. So with dimension of the vector space, to emerge later. Okay. Therefore, we go to the abstract notation of quantum mechanics. Instead of writing Jz V equal to mjz, m times V, that is the eigenvalue equation, where we had the I don't know how big a column vector this is, okay. But what I will do is instead use the quantum mechanics notation. Where we write a ket vector and this causes a little confusion, but the point is the vector V we write as an angular bracket like this, and its label is exactly the same as the eigenvalue it has corresponding to Jz, that is the notation. And so we are not going to write its components. This is in fact abstract notation of this type, but here the vector is labeled by its eigenvalue with respect to Jz. Now we construct J plus and J minus. So have you seen this? This has been done in your classes, yeah. So then we can go a little bit faster. So then we learn that, so who remembers this? J plus J minus is equal to what? Minus plus Jz or plus minus Jz? Okay, so we have to work this out. So Jx plus this is going to be equal to Jx plus Ijy, comma Jx minus Ijy. So Jx will commute, so minus I times Jx Jy. The good thing about the commutator or the Poisson bracket algebras is the linearity. You can bring things out of it, and the bracket of sum is sum of brackets. So that, and then plus I times jy jx, but jx jy is I jz times minus I becomes 1, so I get 2 times jz, one from this and the other from this. Jy jx will be equal to minus I times jz, so I get this. So j plus j minus is equal to 2 times jz and j plus or minus, or rather let us write it as jz comma j plus or minus is jz comma jx plus or minus ijy, that is equal to, that is going to be jz jx is minus I times jy and plus minus I times jz, oh I am sorry, so zx is just y plus I, and jz jy is going to be minus I times jx. So what is this coming out to be now? So we take out plus minus sign, there is this I of course, so it is plus minus I times, okay, plus minus I times j z jy which is equal to minus I jx, so there is another I over here. So that makes, this is a plus 1, so if I take out plus minus, it becomes jx, and because I take out plus minus I get minus plus ijy, which is equal to plus or minus j minus or plus. We agree with this, I times jy, then plus minus, which was just the sign here. So let me put plus minus I times jz jy is minus I jx. So that is equal to I times jy, and minus I and this I, unsigned I put together becomes plus 1. So plus or minus jx. So I take out plus minus out, jx, and having taken plus minus out of this, I get minus plus I times jy. Yeah, yes, not minus plus. Good. Right, thank you. So it is just the same way. Good. So we summarize this by these two things, and I am now trying to wonder if I was supposed to put a square root 2, but square root 2, so to remove this 2, but that 2 is not going to, if I put square root 2's here, then I remove this 2 from here, and the rest of it I'd end up getting a, nothing else would change, right? So we have concluded that thus j plus comma j minus equal to minus times j minus j plus is equal to 2 times jz, and jz j plus minus is equal to plus minus j plus minus. We are sure of all this, right? Yeah, when I take out plus minus sign, that has to also be plus minus sign. Good. So now the statement is that consider the eigenvalue m of Jz and act on it with J plus. Okay. What is this object? To find out what this object is, I hit it with Jz. To find out what it is. But this is same as Jz J plus plus J plus Jz, and then add also minus J plus Jz acting on M. So that is same as commutator Jz J plus J plus Jz acting on M, but the commutator Jz J plus is J plus into bracket 1 plus Jz on M, right? And just this bracket has just become J plus. There was J plus on the left side of this, which I can take out, but then 1 plus Jz hitting M will return M plus 1. So if I have any vector with eigenvalue m, then action of J plus increases that eigenvalue by 1. Now if we do this with minus 1, then I will get Jz on J minus m will be equal to the commutator of Jz comma J minus plus, so this same logic repeats, except that now I have J minus Jz acting on M, and Jz J minus is equal to minus J minus. So that will return me M minus 1 times J minus on M. So J plus and J minus are called raising and lowering operators. Now the point is that there exists a highest value for this M. Okay. So suppose there is a highest value. M, by which we just mean, so we call it L, okay, i.e. M takes values M plus minus 1, M plus minus 2. We saw that this is going to happen, right, when I apply these operators. But its biggest value is some value L. Then we find that to have this happen, we should require that J plus on this L should be equal to 0. You can't raise any further. That is the highest possible value you can have. And if this is true, then by applying J minus to L enough times, we can also check that get the spectrum of eigenvalues L minus 1, L minus 2 separated by integers. Now the point is that in this spectrum, if any number m is an eigenvalue, then so is minus m. Okay. To see this, one other important point is that, so leave this for the time being. The other important point is that the operator, or the, what is it called, the algebra element, okay, J squared, this commutes with all the with Jz and J plus minus, or with Jx, Jy, Jz, everything. This is easy to see because you start commuting. For example, if you take Jx, J squared, the first term would give 0 anyway and would become equal to Jx times Jx comma Jy squared plus Jx comma Jz square. But remember the rules of this commutator. It means that I can take Jy out, one Jy out on this side, and next time I can take out a factor on the other side. You understand this, right? Because this is two factors, A and B. I can take out A on this side and do this. In the next step I take B out on that side, but here A and B are the same. But I have to remember which side I take out A or B. But this is a very, very important property of the bracket. So and this should all add up to 0 because Jx, Jy will give Ijz. This will, so it will give I times Jy times Jz, and here plus Jz times Jy. And here we should get xz is equal to minus I, so I will put a minus sign, Jz jy, right? Jx, jz is minus I jy. So minus, the I is outside, minus sign, and this jz times jy, and from here again minus jy jz. So it is all cancelling, I think. Yes, so it is equal to 0. So you can check that each of these gives 0. So this commutes with each of them. By Schur's lemma, as and when these get represented by matrices on any finite dimensional space, by Schur's lemma, this J squared must be just proportional to a number times identity matrix, because it commutes with all the elements of this. Thus J squared is a number times identity of dimension but now we are trying to find out and also the value of J squared can be found by writing it out as writing this as Jx, the J plus J minus J plus, this, writing these out as product of J plus J minus, and using the algebra again. Okay. Now the main thing I wanted to prove now was that for every eigenvalue m, there is also eigenvalue minus m in the spectrum, and if that is true, so if this is, if we, once we prove this, it is clear that in, so spectrum of eigenvalues is L, L minus 1, L minus 2, etc., and reaches up to minus L. But this also means automatically that L itself has to be integer, because you cannot have integer spaced spectrum which exactly becomes minus L in the end, unless L itself is an integer or a half integer. You can see this by, say, drawing the line, and then say I have L here and I have minus L here. I can only go in unit steps. So either I have to have 0 here, or I have to have 0 exactly between these. So either I have to have 0 here. Here I have what, 1, 2, 3, 4, 5, 6, 7. So I have 0 or I have the 0 in the middle, but these are the only two possibilities. There is no other possibility. Right? So L plus 3 by 2 and becomes plus L, even minus L plus 3 by 2, but becomes L. So these are the only two possibilities for the spectrum. So we need to just check the M to minus M mapping. Moving on for the time being, this means that the space is to L plus 1 dimensional, the dimension that we had not specified so far. Now we will see that if the algebra was really of the L of angular momentum, physically SO3 algebra cannot accept the half integer spectrum as eigenvalues because the corresponding representation matrices will be intrinsically complex and you cannot have that in the real orthogonal group. Whereas SU2 admits both, admits all the vector spaces or all the representations. Each is of course an irreducible representation, and in quantum mechanics, because we believe in complex vector space, spectra are used for half integer spin particles. So the representation space of this can be entirely derived from the algebra alone. So we will see that the next thing, two things I want to do is, one is the Lorentz group SO31 and the other is representation on space of functions. So in quantum mechanics we know that, so two topics for the next time. And to give you a preview, it can be shown that it is isomorphic to SU2 cross SU2. With some inverted commas, okay. Because this is a real orthogonal group. These are both intrinsically complex groups. So if you complexify this algebra, then you can actually make it into this. So if the Lorentz group can be made to look like it is two SU2s, then its representations are also all done, okay. And the trick is very simple actually, so we'll come to it next time. So that is one thing, and the other thing is realizing continuous groups on function spaces. So we have, for example, Lz gets represented by minus I d by d phi and minus I d by d phi on e raised to I m phi returns m as the eigenvalue. So e raised to I m phi is a function space realization of the abstract M we were writing, where we represent now the Lz operator as a differential operator. So these are the two things we'll be continuing with next time.